All right, everyone, thanks for coming for our last stretch of the last couple talks. So very happy to introduce Emo Todorov. He doesn't really need much of an introduction, but he told me to say that he's a person who codes on the beat.
That's because she asked me if I'm still a professor. So I wasn't going to lie. Thank you. So today I'll talk about exploiting the specifics of MuJoCo physics to build a optimal control, learning, estimation, and everything else toolbox that hopefully you guys can enjoy using. I'll tell you a little bit about that new software called MuJoCo, and then I'll go into some technical details. And the device is not doing anything. Okay. So the mission of that software is very broad. Define optimization problems with respect to physics models, MuJoCo, but maybe others, but really just MuJoCo. And solve them efficiently in a user-friendly software environment. It kind of takes inspiration from multiple software architectures and tools that are available. One is the RL frameworks like OpenAI, Gym, etc. So this will just happen. One thing MuJoCo will have on top of these things is a standardized language for specifying cost functions or reward functions. So just like you can ship a MuJoCo model as an XML, you'll also be able to ship a cost function as an XML, independent of Python or any other programming language. The model-based optimization is again like control systems toolbox, Drake, but also content creation too. If you think about your when you do your research, at the end the result is a video, right? Well, there are other software like Final Cut, etc., that produce videos in a different way, but they have very user-friendly features which you guys don't have right now when you produce your videos. Let's put it that. But most importantly, this is meant to be a language for model-based optimization. What's a language, and how is a language different from an SDK? Both have some kind of primitives. Language has primitives that are composable, and you can structure them together to get new meaning, while SDK is not like that. So in particular, it's a parallel interactive environment, interactive in the sense of like Python and MATLAB, that has a standard library of domain-specific classes, domain meaning model-based optimization, that things like models, cost, trajectories, policies, values, etc. The way you compose them is you form these computation graphs. And so here's an example of how you would do MPC. In fact, the thing that you've all talked about, I'm going to show you how that's done in MuJoCo. To make it a language, you want to make the components like at the right size of granularity so that they do useful stuff, but they can also be composed together. If you make them too big, then they become too specialized and nobody wants to use them because they kind of want to change something. So the way you implement MPC, for example, is you need those 6 objects. You have a model, you have a trajectory that's being optimized. You have sample is a sampling-based optimizer. Output is like what you all call residual observation or sensor data. Output can also go into like neural networks and such. You define a cost, and then you put an MPC object on top of it. And you can structure this for many other algorithms. What's an algorithm? So the most learning algorithms you find in the literature, they're basically some kind of pseudocode, usually quite brief, calling or pseudo calling, some kind of functionality that's in principle well understood, but in practice you have to implement it or you have to get a library from somewhere and exchange data. And in fact, if you look at like the average Python code, what does it do? Well, it does a lot of assignments. And then somewhere in between, there may be one line that calls torch to actually compute something, but most of it is just glue between libraries. So I'm seeking to automate that kind of process so that when you're writing your pseudocode, all the pieces that you may want to call, they're just there and you just call them. Here's an example of programming MuJoCo, which is not really programming, but it's like configuring it. So these objects that I kind of briefly mentioned here in that box to implement MPC, you start by importing a MuJoCo model, and you can specify some things. You create trajectories, you create outputs. You use a library that, for example, this says that thing called error is a difference of positions between a site called endpoint and a body called target. And you put losses on them. You can configure trajectory optimizers. You can enable MPC boxes. and so on. So it's a fairly easy, high-level thing. Of course, you have to understand the semantics of what these things mean, but once you do that, it's very efficient to use. I'm not going to do a live demo, partly because these guys asked me to share the screen, and I don't know if it's going to work. But basically, it looks like that. So these objects that you created here, they are populated in a visual environment like at the top right, like those things, and you choose which ones you want to work with, and then they automatically appear in the UI where they kind of have all kinds of options, and they have methods like start, for example, that you execute now. So this is like C++ merged with like a visual environment. So literally your C++ objects appear in your UI. Member variables become little boxes that you can enter. The methods become buttons that you can click, and the visualizer renders the data and shows you what happened. Now, just as a kind of an exercise to see how easy the framework is to use, I imported the MJPC environments in OptiCo. So this is the same model as MJPC. The costs are expressed in OptiCo's cost function format to the extent possible. In case my library is not that rich, and it isn't, because Yuval and company are doing a lot of cost function engineering and have peculiar things that I never thought of. You can have callbacks that run user code. So let me just briefly show you what this looks like. So this is the sampling-based optimizer. This thing works really well. Sampling, this is a Acrobat. It struggles. This is a really hard task for sampling NRL. This is the little walker. You can perturb it, and so on. So what OptiCo does is it has a thread pool that it manages. So parallel computing happens like automatically. You don't have to do anything about it. Because the costs are evaluated in OptiCo, the costs also run in parallel. So basically, there's no Python in there to serialize anything. Everything is completely parallel. Every object automatically parallelizes itself if it can. And like Yuval said, it's pretty amazing that these things actually work. This is the silly sampler that Yuval said. I mean, my sampler is more elaborate, but turns out it's not needed to enable the elaborate features for this one. Okay. Now, let's talk about... So sampling, it's available in OptiCo as plan B. There's an old saying that evolutionary algorithms, which are a form of sampling, are the second best method for every optimization problem. I did not make that up. That's a very old saying in the community. I want to make a few comments about sampling. Let's look at how you do imitation learning or maximum likelihood estimation. Like you collect a bunch of trajectories from somewhere, you are trying to fit them with some policy that would reproduce those trajectories. This log Python here is just the difference between what your policy said and what the action actually was, and you average the errors and you do gradient descent to that. Now, what does reinforcement learning do? Actually, does exactly the same thing, except the trajectories are generated randomly instead of acquired from a human, and they're weighted by the rewards. So if you want to match policy gradients to maximum to imitation learning, just assume that the human only generated trajectories that have reward 1 and kept the bad ones to themselves and did not put them in a database. So the two are actually exactly the same thing, it's just the data set is different. So in both cases, the learning controller imitates good trajectories from a data set. In RL, however, as we know, reward can increase and even asymptote sometimes, while even the good trajectories, according to the reward function, good, remain like qualitatively undesirable, like this orientation task. Like it's amazing that it can shake the hand and the cube gets there, but the human would not do that, and you would not probably want a robot to really do that if you put it in somebody's home. Like in your lab, it's okay to shake. So we need to fix that before everyone goes off to do imitation learning. Or are we too late? I don't know. Another comment I want to make is the relationship between policy gradients and the sampling MPC. So policy gradient, as noted here, is offline imitation of random trajectories that are weighted by reward. Offline meaning like you learned offline, and now when you're running, you're imitating some trajectories. Sampling MPC is the same thing, but online. So right, you're generating a random trajectory, picking the best one and imitating it by literally playing back the first reward. Which leads to the observation that you can actually combine it. So you could use like adaptive policy gradient to do an MPC. What does that mean? Take any trajectory, do very quick overfitting of the policy parameters to the current state you're in, execute the action and keep going. I actually implemented our linear policy. It looks quite promising. So you can think of a policy as an implicit representation of a trajectory, and then that's how you optimize it. And final note I want to make is that I think it's a really valid question. Is it more efficient to sample in action space, which is what CoRL does, or directly in policy parameter space? Meaning you have a policy, you perturb parameters somehow, go ahead and evaluate the policy deterministically without any more noise, and that's a sample. There is a paper from Ben Rex group in Berkeley, which has pretty good evidence this is actually a bad idea. I know there's going to be a lot of psychological resistance to this notion because it would suggest that a lot of people have wasted a lot of time over decades. But that doesn't mean it isn't true. So that is anyway. All these things are going to be available in Optiful. Now let's talk about plan. Analytical derivatives, obviously. I would say that the finite differences are like Plan B 2.0. It's great that we have them, and we use them until we get our act together and write the actual derivatives. Do you need to? Sometimes you need them, sometimes you don't. But when you need them, if they're not there, you end up doing something silly in your pseudocode because it requires you to call some functionality that isn't there. And then you're going to use something else, and you're going to spin some silly story of how the other thing you did is the right thing, even though it's not the right thing, you just didn't have the thing that you needed. And that happens all the time. And I'll give you a specific example from our lab. Trajectory optimization, as I think other people mentioned, this alone can get you stuck with problems that have context. So if you have analytical derivatives, you're only going to get stuck faster. So you need to do something else. That's something else which I'm really interested in that I'm going to emphasize is problem transformations. Meaning, if they understand doesn't work or whatever, make the problem easier. Continuation methods are one of those. I'm going to talk about some other ones. And finally, model-based learning, like Bellman residuals and state value functions. Now, RL is model free, that's great, but if you're going to use it with a simulation model, you have a model by definition, might as well utilize the model more fully. In terms of analytical derivatives, so MuJoCo has forward and inverse dynamics. Forward dynamics is a mapping from position velocity and applied force, tau, to acceleration A. And that's solved by convex optimization with like the Newton method, etc. Inverse dynamics is actually an analytical formula. It maps from position velocity and acceleration to applied force. Now, I have the exact derivatives of both of these functions with respect to the second two parameters, velocities, forces, and accelerations. The derivatives with respect to position are approximate for now, approximation meaning that the contact Jacobians are treated as constant, which they're not, they depend on position. Why is that? Because collisions are nasty. So computing exact derivatives requires contact Jacobian, like differentiable collisions. And that's possible because MuJoCo actually has geometric primitives for collision, and they can be differentiated, and I should. But there are other things that are hard to differentiate, except for a paper for this, our wonderful French colleagues who seem to have figured out a really good way to do it. Now, let me just say that this paper kind of suggests sampling. For me, if you're going to use sampling and you have a deep computation stack, sampling belongs at the top. Like, I don't want to put sampling in the middle. Which is kind of what they're suggesting. They have some good results. At the end of their paper, there is a method which basically replaces a max with a softmax and makes things differentiable. They motivate it through sampling, but you can forget about sampling. It's just a completely deterministic thing. So that's my favorite, and I may actually implement it. Now, trajectory optimization in direct method in MuJoCo benefits from the fact that MuJoCo has inverse dynamics. And it can also do inverse control because the control model was designed to be affine, so to be invertible. Basically, this is baked in. How does that work? You represent trajectory as sequence of poses. You define differences in time to get the velocities and accelerations, run inverse dynamics to get forces, and the inverse dynamics also gives you everything else, like constraint forces, whatever. You impose constraints on those forces to make sure they're actually realizable by your actuators. In this case, it's a Gauss-Newton method to apply to the augmented Lagrangian. Let me show you a couple of simple examples from earlier versions of MuJoCo. Click run, solves Acrobot in 30 milliseconds. This is a trajectory. This is a hopper. This is the initial trajectory. It's just kind of sliding up and down. Click run, it solves it in about 300 and some milliseconds. This is trajectory it found. And since it records all the data, you can now review what the solver did. These are all the trajectories that it did over time. This is something about the gradients, but I'm going to skip that. So, right, so this is really fast. You've already mentioned how do you parallelize shooting method, like you shoot, which is serial, and then you can use it to compute a finite difference thing on multiple cores. Or if you have analytical derivatives, though, not clear what to use them. Well, in direct methods, here's what you do. We have a trajectory. There is no serialization. You're not integrating anything. You're representing a trajectory directly. So you can break the trajectory into pieces in time, process each piece on a different thread, compute everything you have to compute. At the end, there's one serial thing, which is you basically have to factorize a band diagonal Hessian, which happens to be about like 80% of the work. So it's nothing. So these direct methods are very much amenable to multi-threading, even if you have analytical derivatives, which is what I'm exploiting here. Now, these problem transformations I promised. So this is the RL view. You have an agent, you have simulator, not the world. World/simulator generates the next state. It feeds into both agent and the state. Now, let's open up that simulator box and see what's in it. Roughly speaking, this is what's in it. There's some preparation phase where you do collision detection. You compute various quantities that are needed for the consequent phases. You evaluate the actuation model, figure out what forces your actuators are generating. Then you pass, then these first two stages construct an optimization problem, which is passed to a constraint solver, which is like Newton method. That gives you an acceleration. Then you do a discrete time integrator and you go. So here's what we're going to do. We're going to make our agent a lot more powerful. We're going to give it extra controls so that it can literally reach into the simulator and start tweaking how the boxes of the simulator work. So in some sense, the agent is choosing its own physics that it's working with, and then it will get penalized for that. And that's how we do continuation and other things. So in particular, there are three such things. They target those three boxes, and they have cute names. They're called deform, remote, and go. Here's what intuitively they do. Deform, I think, has some vague resemblance to contact implicit optimization. Not exactly, but there is a relationship. So here's the idea. We allow the agent to modify the optimization problem that's passed to the constraint solver. And in particular, it can make some constraints soft, like on demand. Now, normally, you can do continuation where you soften all the constraints. In fact, MuJoCo has like override modes to do that, but now you're doing it up front. In this case, we allow the agent to decide at some point in time, some contact is getting in the way. So, okay, contact, please get out so I can get to my goal, and then I'll talk to you later. Basically, that's the reason. That's deformed. Remote is kind of a reincarnation of the contact invariant optimization that was done earlier in my lab. So here, the idea is the opposite. If you need some kind of contact, but it's not there. Let's say I want that glass pushed forward. If I'm here, no amount of sampling will really get me there, right? I mean, or if it's huge sampling. So what I want to know is somehow to discover that it will be beneficial to make contact with that glass. This thing does that. It makes it possible for optimizer to discover such things. And the last one, goal-directed dynamics, it actually replaces the solver with a different solver. What this does is that we're going to allow the agent to pass controls that like are on a high level. In particular, they specify how they would like the system to accelerate. We don't know how to make it happen, but it's what we would like. And then a low-level solver will figure out, okay, this is how you want me to accelerate. What controls can I pick to make it accelerate like that to the extent possible? And then I run the solver and figure out what the forces are. This is something I developed a while ago. It's called goal-directed dynamics. Now, once we're done with that discussion, we can close that box again. And now we have an agent, which is talking to a modified simulator with modified states and modified controls. But to the rest of the optical universe of compute classes, it looks like a dynamical system. So what optical does has standard interfaces where, let's say, what's a dynamical system? It's not necessarily a MuJoCo model. It's some kind of class that supports certain functions and the virtual functions that are implemented. Those functions are tailored to MuJoCo. For example, inverse dynamics is expected to be provided, which basically means you cannot put any other simulator. But there are things you can build on top of MuJoCo that are valid. And so like all these things basically end up looking like a modified dynamics. which means that like you can do the sampling MPC, you can do direct optimization, you can do policy gradient, whatever you want. You just target that to modify dynamics, and all of a sudden the algorithm works. But let's say put the CIO or goal-directed dynamics under the hood. Let me talk a bit more about those 6 stages. So the original idea of contact divided optimization, or CIO, was that it's kind of a physics, cost, and optimization combined in one in a brilliant way by Igor Mordak. Nobody ever understood what he did, but it produced amazing results, which you may have seen. So these are entire trajectories, very long ones, which were planned as one by a trajectory optimizer with very simple cost. Like basically this thing says like put your body over the cross and be upside down. And all these contact sequences emerge completely automatically. No contact scheduling, no nothing. Gets out of the, you can do markation, thing like, so here the cost is to put the head of the little guy at the top up there, and these things figure out how to cooperate. And so on. So this has been out there for like, what, 10 years now. Probably remains now the most impressive examples of fully automatic movement generation. It's hard to implement, and also it was kind of slow. So these things were taking 5-10 minutes to compute one of those movies. I want them to be much more responsive. So what I've done is I found a way to reformulate this, basically using unusual actuators and unusual control costs, which are added to the MuJoCo model. Once I add those things, I have a modified dynamical system, but it's still a dynamical system. It still checks all my boxes of what a dynamical system should be, and then any optimizer can run on top of it. So here's a little, very trivial example for now. Here, what's happening is that the red mass is actuated, the green mass is not. The cost says the green mass should go to the white mass. And this thing discovers that it's a good idea to go hit the green point mass in like one iteration of Gauss matrix because of magic costs that are baked into a system that we're able to guide. Here's another one of those problem transformations. So this goal-directed business. So here's what it is. So MuJoCo forward dynamics, let me unpack it a little bit more, is defined as the argmin over accelerations of some function. That function is a convex function R over accelerations. The minimum of that function is the passive dynamics of the system. And then you add to it a dot product between the acceleration and the applied force tau. You minimize that and you get the acceleration. Those of you who like math should recognize that expression out there. What is that? There's a duality called Legendre duality. So this is how you construct it. I'm not going to talk about that because I'm out of time, but it's a really beautiful mathematical entertainment. Inverse dynamics in MuJoCo is just the gradient of that function. That's why it's analytical. Goal-directed dynamics says this. We're going to, so here both dynamics and the forces are modified. We're going to use the control cost. So this is acceleration. This gradient of R is the applied force. We're going to square it, and we're going to subtract this thing from it. And we're going to take argmin, but only over accelerations that are feasible, meaning that our actuators can implement. So you can see the two are kind of related. So this is a non-smooth, non-convex constraint optimization problem, really nasty, but I have a solver that solves it only about 50% slower than MuJoCo forward dynamics, which is smooth and convex and constrained. Kind of strange. So here's the illustration of that. Here I'm guiding this thing by telling it that the selected body should accelerate towards the red target. And it's figuring out what controls to use in order to make that happen. So it almost looks like I have a virtual force pulling on it, but there is no force. I'm simply telling it what I would like. And this is a completely greedy, like instantaneous solver that says, how do I coordinate my whole body? How do I utilize the contacts with the ground such that I accelerate the way that the user told me to accelerate? In this case, the guy controlling the mouse. You can also do things. So this is a generalization of task space or like end effector control, but it's a pretty big generalization. And again, this is now in the new optical, this is a modification to dynamics. Now I can put RL or sampling on top of that. And now let's say the sampler is not going to be sampling controls, but it's going to be sampling desired accelerations. And this is, well, not as fast as MuJoCo physics, but almost as fast. So now you can do hierarchies out of it. Finally, model-based learning. So I think this, like I said, this I think is really important. Here's a specific example that's something we did a while ago. So this combines MPC through sampling with value learning. So MPC, you normally add up some costs, but now here we're saying, okay, what's going on? Why is this here? I don't know. Okay, you add up your cost over trajectory, then at the last time step, you evaluate a cost to go or a value function, and you add it to MPC. That's going to overcome the myopic nature of MPC and allow you to kind of look into the future. Where do you get the value function? Well, you learn it by minimizing Bellman residuals along trajectories that were generated by MPC. And then the two keep improving. And the Bellman equation, so the value function basically is this. Here's what this method did. It's pretty cool. So here the task is to move the box over there, and this guy goes there, pushes it heroically, and then. So it turned out to be a lot more, like 10 to 100 times more sample efficient than forestry gradients. Now let me tell you a funny story about this. So why on earth is this thing using sampling MPC, given that, you know, I mean, I developed the algorithm method like 20 years ago. Yuval and Tom scaled it up in my lab and did really good full body MPC in 2012. Everyone in robotics thinks we have thought that we lost our mind, and now it's running happily and on the Unity humanoid downstairs. Do you know the biped, the company representative told me that thing is running MPC through MuJoCo in some proprietary way that they're not going to tell me about. So why would you put sampling when you put LQG? Like you can see in, like if you load MJPC and you compare sampling to LQG, you'll see that LQG is actually better for these tasks, not for the hand orientation task, but for this. The answer is that we're close to paper deadlines. I could not convince the students involved in this to do proper MPC. This thing works out of the box with minimal effort, so that's what. And these are really good students. I mean, these are like really, really good people. If we had Optico, that would not have happened because that building block would have been there. The pseudocode would have just called the right box and things would have happened. So, like I said, I suspect quite a few algorithms that we know about would have been quite different if people didn't have to implement everything themselves. So it's important to have that. Finally, this thing here that you need to optimize in the Bellman equation, this is equivalent to one-step MPC or optimization of the Q functions over controls. And our goal-directed dynamics solver solves exactly that thing, where the goal, the top high-level goal, is simply the gradient of the optimal value function, which has interpretation of applied force. So in general, there are many ways to combine policy, value learning, trajectory optimization, demonstration data, while using those in the loop solvers. Optico is designed to make all of that easy, and hopefully it will. We'll see. Thank you.
We have time maybe for a couple of questions.
Yes.
Yeah, how sensitive is this to the initial conditions, like for CIO, for example, it's some capital setup, right?
CIO was very robust, as I recall. The problem is that it was slow. It was robust but slow, not at all sensitive. What's sensitive to initial conditions? Let me think. I don't think anything is particularly sensitive to initial conditions. I mean, if you get stuck, the problem is not to get stuck, right? I mean, optimizers, you know, if you start in the wrong basin of attraction, that's another reason. But yeah, I wouldn't say initial conditions are an issue.
But is there a way to define like a rough outline of the trajectory that you then can refine and optimize?
There is a way, yes. In fact, it has an inverse kinematics tool that literally allows you to edit trajectories, start from there, and go. Let me see if I can find. I want to show. I cut that out of the talk, but since you asked, I want to show it to you. So here, there's an IK tool. You select body parts. You can pin them in place. You can drag the thing around. It has kind of a physics-based IK, basically. You can design libraries of initial states. And then here is what's that? Here's the trajectory design. So here I'm showing the whole trajectory. Now I'm going to select one body part at one point in time. going to drag it, and it's going to stretch the Hauff ejector. So yeah, it's like I said, I want Blender-like functionality in our field. I want to make it easy to design it. Please don't use it to cheat. Like, don't report in your paper that trajectory came out of your control and you did IK. I'm not responsible for any, ethics violations. But yeah, okay. Anything else? Yes. Either way, go ahead.
The part that you say that you changed for the dynamic in order to hold it,
The goal-directed one?
yeah, that's like
Mhm.
reform. So basically, you're changing. Essentially changing dynamics in order to find a solution.
Mhm.
How you change it back?
Okay, so in the goal-directed one, I don't have to because the thing is specifying goals. My fancy solver is computing a feasible control which drives dynamics forward. So it's simply a control transformation because mapping into a feasible control. In the other two, the remote and deform, it's a continuation problem. So I have a parameter that goes from 1 to 0. When you drag it to 0, it is mathematically guaranteed to be the exact same thing. So in continuation, what's continuation? Like you have some nasty optimization profile, you're stuck. So you find some way to transform your nasty function into a simple one. You optimize that one, and then you turn a knob that gradually morphs the simple function into your original function. And then the hope is that you're going to track the minimum and land into the minimum of the original function. So that's a very general idea in optimization. These two dynamics these two problem transformations that I mentioned here, deform and remote, these are continuation methods. The red one is not. It's a control transformation method. You were saying?
For the panel.
That's
Okay.
great. All right, let's thank Emma one more time.
Thank you. Okay.